Hello and welcome to the Unit 6 podcast on Section 13.1. I'm Mr. Sakaguchi,
I am Mr. Lin.
and today this unit is all about gases.
Yep.
There are a theory behind the way gases behave, and there are assumptions that we're going to basically make, so that way we can use simple equations to kind of describe their behavior in this unit. We'll talk at the end of the unit the difference between these assumptions versus how gases really behave.
Right. So these are all theoretical and ideal versus how real gases are. So one of the first assumptions is that the gas particles don't attract or push away from each other. They're non-interactive. They just bump into each other.
The next assumption we make is that particles do not occupy a significant volume. So in other words, we don't have to take into account the volume that the gas particles themselves occupy in the container.
And since gas particles are so energetic, they're always moving. They're constant in their motion and very random.
The fourth assumption we make is that collisions between particles are elastic. What that basically means is that the energy they have when they collide is the energy they have after their collision with something else.
Then the kinetic energy, energy of motion, is dependent upon the temperature. So the hotter something is, the faster the gas particles are moving, and conversely, if the temperature is lower, the particles will move slower.
And then the last assumption we make is that the average kinetic energy is constant. So in other words, if we have a mixture of gas, the kinetic energy is on average the same for both or several different kinds of gases in the mix. Now, it's one important thing to note is that even though we're making these assumptions, under most conditions, these are actually true for gases. There are some special circumstances where this may or may not be true, so don't think like this doesn't apply at all.
And other than the exceptions, the assumption is that this theory applies to all types of gases regardless of its chemical composition.
Okay, some physical properties of gases. They have low density. They can be expanded and they can be compressed.
They have. Oh, okay, go ahead.
Sorry, go ahead.
I was going to move on to the next one, which states that gases have indefinite volume, meaning that you can change the amount of space that a gas can take up. And there's also something called diffusion, which you probably learned in biology previous year, where gases will spread randomly just based upon density, like where it is starting out, and it will spread out until there's an even distribution of gas particles everywhere.
Moving along those lines of diffusion, we also have something known as effusion. Effusion is basically movement of a gas through a small opening. If we have average kinetic energy and we have two gases that are mixed together, we can calculate the difference in their velocity or movement within a container by using Graham's law of effusion.
What this gives you is just a ratio of how one gas is faster or slower compared to the other gas that's in the container, and this is dependent upon the mass or heaviness of the compound.
What's the inverse of the mass, right? So
Right,
notice
inverse.
how rate of A over B is B over A, and there's a reason why, but it's not really important that we derive this. But it allows us, as Mr. Lin said, is to kind of have a comparative difference in terms of rate. So, for instance, one gas may move at twice the velocity of the other one. We can see that's a function of mass. One other feature of gases to be aware of is pressure. This is force per unit area, and basically, when gas particles collide with their on the ends of the container that it's in, it exhibits this thing known as force.
So let's say you take a basketball and you feel the pressure of the basketball, what's really going on is that the individual gas particles are banging against the walls of that basketball collectively. And that's what you're feeling as pressure. And this occurs in all directions of its container. When it's an open space, like in our air that you're breathing, that's called atmospheric pressure, and it goes in all directions, up, down, left, right, whatever.
Atmospheric pressure is measured with a barometer. You probably, if you ever watch weather reports, you hear barometric readings. That tells you the difference in pressure. Sometimes that can give you indications whether or not it'll rain or whether tornadoes or other certain kinds of weather are going to come. In terms of units, we measure pressure with many different units that are you'll see throughout this chapter, or unit I should say. Sometimes we measure pressure in atmospheres, sometimes in kilopascals. Kilopascals is actually the SI unit of choice. And then on TV and stuff, you might see inches of mercury, which is related to millimeters of mercury. And then there's also torrs. And a torr is basically the same thing as a millimeter of mercury.
Right.
But hopefully if you remember your dimensional analysis, you'll be able to freely convert between atmospheres, kilopascals, torrs, and millimeters of mercury.
And we'll practice that in class as well.
One other thing we want to talk about here are partial pressures. Basically, if you have a mixture of gases, they all have their own pressure, and their pressure is independent of the other gases that are in the mix. What we find is that the total pressure is the sum of the partial pressures of each of the gases in the mix. So P total, which represents the total pressure, is the sum of the partial pressures of all the components that are in the mix of gases. Here in this figure on the bottom, you can see that oxygen, nitrogen, argon, water, and carbon dioxide, these are
The primary gases in our air.
and these are the roughly their pressures in kilopascals, and it adds up to 101.3.
That's pretty much it. Till next time.